In this video, we're going to solve a problem from the Cambridge Step 3 examination. Here we have four definite integrals, and we have to prove that they are equal without computing the actual values. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. So now we have four definite integrals, and we cannot compute their actual values, and we have to show that they are equal. So that restricts us to only two elementary tools. The first one would be choosing some right functions to do some substitutions. While the second tool we have is to do integration by parts. I usually follow the LIATE rule, which means the preference of picking functions as part of to do the integration, followed by logarithms, inverse functions, arithmetic, trigonometric, exponential. Some viewers suggested to use the ILATE rule instead, but it's really up to your preference. I usually go for the first one, but anyway, just a sharing of my preference. And then the last hint before I really start working is that I suggest that you can take a look at the limits of the integrals. For example, if I'm trying to show that this integral v is equal to the integral u, so we have limits 1/2, 1/3 versus log 3 and log 2, then one substitution might be consider rewriting, say, u to be equal to minus log v, something like that. Then we might be able to proceed slightly faster than usual. So to solve this problem, I'm going to show the following. I'm going to show that u and v are equal, and then t and v are equal, and finally u and x are equal. So I'm going to start with the easier one, which is u and v. So let's see how they can be equal. Now, as suggested just now, from the integral v, I can say that it's equal to, by rewriting v equals e to the power u, and then of course you can say that u equals log v, and for the differentials we have dv equals e to the power u du. While for the limits, when v equals 1/2, u equals log of 1/2, and that's minus log 2. When v equals 1/3, u equals log of 1/3, and that's minus log 3. So the integral can be rewritten as minus log 2 minus log 3, and then for log v it becomes u, and then it's divided by 1 minus e to the power 2u, and for dv it becomes e to the power u du. So that's the new integral. Now we can simplify that a bit, and in fact it becomes minus of minus log 2 minus log 3 for the limits, and then u over e to the minus u minus e to the power u du. So now we are actually very close to the integral u, because in fact sin u by definition is just e to the power u minus e to the power minus u over 2. So that means we have minus log 2 minus log 3 for the limits, and then it's u over minus 2 sine u du. Now looking at the integral u, our limits should be log 3 at the top and log 2 at the bottom. So let's flip the limits, and we have minus log 3 at the top now, and then minus log 2, so it's slightly closer, but we are still having the minus sign at the limits. So why not I just replace u by minus u, so the limits can be fixed. However, now as they are replaced, I need to move the differential as well. It becomes minus du. And then we have minus 2 times sine minus u. So it remains to fix the minus signs. And they can easily be fixed. And so there we have the integral we want, and that is u. So we've managed to prove that v and u are actually equal without computing their actual values. So now let's move on to the other two parts that I want to show, which is that t equals v. So for the second part, I'm going to show that integrals t and v are equal. To show this, I'm going to use the integral by parts. So for t, I'm going to let u to be equal to arctangent h t, and now to differentiate it. So in fact, by definition, I can say that tan h of u is equal to t. And when I differentiate both sides, I actually have secant h squared u and then du dt to be actually equal to 1. And in fact, secant h squared is just 1 plus, so it's not 1 plus this time, it's 1 minus, because to derive it, I can go back to cos square u du equals dt. And in fact, for hyperbolic functions, we have cos squared minus sine squared to be equal to 1 instead of plus. So that means it's actually just 1 minus tangent x squared of u. So that means the so-called du is actually 1 over 1 minus t squared times dt. And so this is the thing that we want to apply integration by parts. And the second part is easier, is that the other part of the integral dt over t, I let this to be dv, let dv equals this, and so v equals log t. So to apply the rule, we start with u dv, and it's going to be equal to uv, which is log t times arctan h of t, under the limit 1/2 and 1/3, subtracted by v du, and that is log t over 1 minus t squared dt, under the limits 1/2 and 1/3. And this is actually really close. This part of the expression is really close to the integral v. It's just the variable that I have to change from t to v, and we are done. So it remains to show that the part that wasn't highlighted, it will really take value 0. So in fact, the expression above equals log of 1/2 times log of 1/2 times arctangent h of 1/2 minus log of 1/3 times arctangent h of 1/3, and then minus the integral that we want. So let's see whether the part labeled in yellow will take value 0. So let's see down below. Now to compute the value of arctangent h of 1/2 or arctangent h of 1/3, we need to know how arctangent h, this function, actually behaves. So if I'm going to let y to be arctangent h of, say, 1/2, or I should say in general of t, then again by definition I have tan h y equals t. Then recall the definition of tangent h, we have e to the power y minus e to the power minus y over e to the power y plus e to the power minus y equals t. So rearranging the fraction, we have t to be actually equal to this fraction. I actually multiply the numerator and denominator by both by e to the power y. So then the number of y's that appear in the expressions will be reduced. Now next I'm going to rearrange and make y the subject of the equation. So now I have e to the power 2y equals 1 plus t over 1 minus t, and I can take log on both sides, so eventually I get this expression of logarithm. So now back to our expression, we have log of 1/2 times arctangent h of 1/2, and that is simply 1/2 of log 1 plus 1/2 over 1 minus 1/2. And we do the same on 1/3. Of course, we do not forget the integral that we need to compute. But for the logs above, if you look to that closely, you will notice that is log of 1/2 times half of log 3, and then minus by log of 1/3 times half of log 2. And they will actually be the same, because log of 1/2 is just minus log 2, log of 1/3 is just minus log 3, and they are actually the same. So we only have the integral that we want to remain, and so we've managed to prove that integrals t and v are really equal. So now after doing two operations, we've managed to show that t equals v and then v equals u. Now it remains to show that u equals to x. So let's see whether it's really true. Now to show that these two integrals are equal, I'm going to start with the integral x. And I'm going to rewrite cotangent h of x as 1 over tangent h of x. And so it's actually just minus of the integral of natural log of tangent h of x dx. So from this, at this point I'm going to use integration by parts, starting by letting u equals log of tangent h of x, and then du will then become the fraction with the bottom to be tangent h of x, and what for the top is secant h squared of x dx. And simplifying, we will have 1 over sin x and cos x times dx. Afterwards, I'm going to let dv equals dx, and then integrating I have v equals x, so I can proceed with the integration by parts. So from this I have u dv equals uv, so it's x times natural log of tangent h of x, and this expression evaluated under the limits half of log 3 and half of log 2. This value is subtracted by the integral of the same limits, and for this we have v du instead. So x over sin x and cos x dx. And in fact, we are really close to the integral u already, because this part of the integral, the denominator, is, I can replace that by half of sin 2x. And so I have the numerical part to be half of log 3 and then log of tangent h of this value again, minus similar things, added by the integral of x over 1/2 of sin 2x dx. So for just the integral, I'm going to ignore the log part for the time being. I can rewrite the integral as 2x over sin of 2x dx. And if you look back at the integral at integral u, it's really close. I'm just one very simple substitution away, which is to rewrite 2x as u, and then we will be done. But before that, let me also take care of this part of the expression, which is to compute log of tangent h of certain numerical values. So we call that tangent h of x is e to the power 2x minus 1 over e to the power 2x plus 1. as we have done before. Tangent h of half of log of 3, say for example, is just e to the power log 3 minus 1 over e to the power log 3 plus 1. And so that means I will have 3 minus 1 over 3 plus 1, and that's just 1/2, a very simple value. So from this, I can further proceed by writing the green part as minus of half log 3 times half of log 1/2 minus half of log 2 times log of. You can do that yourself and you will eventually get 1/3. And then plus, as I've said before, I'm going to replace 2x by u. And so I'm going to get log 3, log 2 at the limits. And then u over sine u. And then dx is just half of du. And so for the numerical part, we have 0. You can quickly see that. And for integral, it eventually becomes the integral that we want. U over double of sine u du under limits of log 3 and log 2. And that's exactly u. So altogether, after all these operations, showing that 3 pairs of integrals are equal, I've managed to show that t, u, v, x, all 4 integrals are equal. And so I've finished this step problem.